All right, so going on this idea of acid strengths and structures, we're now going to take a look at oxoacids. Oxoacids are basically acids that have some sort of oxygen in it. So just to recap a little bit, if the central atom, that's these oxoacids are connected to, are from the same group and have the same oxidation number, as the acid strength increases, it's going to increase with the electronegativity of that element. So again, kind of talking about this idea of the pull. Now, this is a little bit different from using the halogen example. Okay, so again, in the halogen example, it was a little bit more about the weaker the acid, it's because the fluorines are more highly electronegative. So because of that, you end up having a weaker acid. But here, it actually changes a little bit. As you increase that electronegativity, you end up increasing the acid strength. So what ends up happening is that OH bond tends to break a little easy. So here's a great example of this, HOClOO. Now, for the most part, chlorines are going to have a very strong, most of the chlorines are going to have, especially with the oxygens, are going to have a very, very strong electronegativity to these electrons. So what's going to happen is that they're going to pull on the oxygens here. And because of that hydrogen is going to get kind of neglected a little bit and it's just going to fly off. And because of that strength of that acid is going to be very, very strong. Here's another example, HOBROO. Okay, in this specific example, bromine is obviously a highly electronegative element. So because of that, it's going to start yanking on those O's, and because of that, then again, the OH is going to be easily donated away. So always look at these simple atoms on the inside, especially if you see things that actually have a central atom as you draw these dot structures of how they're approaching this idea of acid strength. Okay, bromine, chlorine. Chlorine is more electronegative than bromine. Again, as you're kind of going up the group here, you're going to get more electronegativity. So I would expect the bromine molecule to definitely be a stronger acid in this specific case. However, when we take a look at chlorine, right? So chlorine is actually higher on the scale. I think I made a little mistake on that one. So as you get higher on the group, chlorine is going to pull on those electrons. And because of that, it's going to have a stronger acidity than something like HBrO3. Okay, so as you're drawing these Lewis dot structures, keep that in mind about that. So again, your next question is, why are the oxygens, the contribution of these oxygens and these acids determine the strength of these acids? Okay. All right. Second, the oxoacids have the same central atom, but they have different numbers of attached groups. So what about in this specific case? So for example, as the acid strength increases, as the oxidation number of Z increases. So we're going to be talking now about electronegativity and switching that over to the definition of what an oxidation is, which means basically the transfer of electrons from one side to the other, either a reduction or an oxidation where they lose electrons. Now here's a great example of this. Hypochlorous acid is HOCl. Okay. Now what ends up happening in this specific case, if you take a look at the oxidation number, you have a +1. Okay, so an overall oxidation for the Z atom. Okay. Now, if you take a look at specifically, and we're looking at the oxygen, obviously. And if we take a look at chlorous acid, you keep on increasing these numbers. Now the oxidation number even increases even further. So on chlorous acid, you're going to lose 3 electrons. In the chloric acid example, you have HOClOO. Now, again, this only works if the atom is actually the same. So we're looking at that chlorine atom, sorry, not the oxygen, we're looking at that chlorine atom. And that chlorine atom is going to have a different change in oxidation as it begins to add different groups to it. So the last one's called perchloric acid. And this one has a +7 on it because it does have more oxygens to it. And because of that, the oxidation number changes for that overall for that chlorine. So that's going to be a +7 oxidation. So in this specific case, perchloric acid will still take the cake in terms of the oxidation. So the order would be HClO4 greater than HClO3 greater than HClO2 and greater than HClO. And because of that, then what you end up having is a situation where these perchloric acids, these chloric acids, end up being much, much stronger, because as you keep on attaching stuff to the central atom, in this case chlorine, you're going to definitely start creating situations where these electrons are going to start flying off. Okay. All right, let's talk about neutral solutions basically. So on a neutral solutions, you basically are going to have a salt being produced by an alkaline earth metal and the conjugate base of a strong acid. So specifically something like an NO3 or a Br. So in a salt, for example, if we take a look at something very familiar to us like NaCl, Na is obviously an alkali metal, and if you throw in a Cl, which is basically the conjugate base of a strong acid, you end up with a neutral solution. Now, for example, take a look at here, as I was explaining earlier, NaCl solid, you add in some water, you're going to make Na plus and Cl minus ions. Now, this actually comes from this idea of the hydration of sodium chloride. In the basic solutions, the salts are derived from a strong base with a weak acid. So let's just give you an NaOH and plus, let's say, acetic acid, then you end up getting a basic solution. Okay. So here's sodium. This is going to be sodium acetate, which is basically your acetic acid derivative. You add some water in it, and you're going to form a basic solution in this specific case. So if you actually take a look at this, you're going to get Na plus ions and the CH3COO minus, turning that solution basic because you have that CH3COO minus floating around. Now, if you actually go ahead and dump some water in it, you pretty much are going to react with the water, and then that's going to produce your hydroxide. So that's where you end up getting that basic solution that you end up having. And so when you're taking a look at examples like this, right, you always want to ask yourself, how can I make a solution basic or acidic? And if you're going to be adding a very strong base and a weak acid, you're most likely going to end up with that hydroxide. And in the titration examples, it's a great one to consider as well. All right, so let's talk about the acid properties of salts. So salts are derived from a strong acid and a weak base. So again, let's take a look at something like HCl, right? If you actually, NaCl, actually not NaCl, couldn't be that one. If you add in a very strong acid like HCl, you throw in a weak base, you know, something like caffeine or something, you're basically going to make a more acidic solution salt. And so here's an example of ammonium chloride. Okay, so you're going to get a weak base, you're going to throw in a strong acid in there, and then you're going to make that. So what ends up happening is you end up getting a situation where the NH4 comes in, and then it breaks down one time further into NH3 and H+, creating your acid solution. And because of that, salts with very small, highly charged metal cations like Al3 and the conjugate base of a strong base usually end up being great examples of something where you get this acidic solutions, right? So that's something to really consider as we're kind of moving forward about how you can make these different solutions acidic or basic. All right, so here's an example of acid hydrolysis of aluminum. So you got aluminum, H2O63 plus a little bit of water, throwing that in, and water basically kind of interacts, forming a new compound here. And so when you're taking a look at salts, for example, this is a great example of something where the salts are cations from strong base and anions from a strong acid. So for example, NaCl, usually the pH is approximately 7. So if I'm making salt water on a neutralization reaction like NaCl plus OH, usually your pH is going to be a 7 in a regular titration type. However, if I change this a little bit and I make a strong base, and let's say an anion from a weak acid, let's take a look at this, then you're getting into a pH that's greater than 7. Then what you're going to end up having is a stronger NaOH presence in there, which in other words, the pH is going to be a little bit higher. Now, if I take a look at a cation from a weak base, and then an anion from a strong acid, in this specific case, you're going to end up getting something like a pH of less than 7. So this is something very important, especially when you're doing titration curves, because depending on the combination you're going to make, weak acid, strong acid, with a strong acid or weak base, you're going to get these salts that are going to start showing up. They're going to be adjusting that pH. And the last one is we have a weak base and a weak acid. In this specific case, it really depends on the Kb and the Ka values. And then smallly charged cations, usually they're called hydrated cations, are going to be less than 7. Okay. All right. So the first one, solutions which both the cation and the anion hydrolyze, the Kb for the anion is going to be greater than the Ka for the cation, the solution will be basic. And in this specific case, and it kind of makes sense, right? So if your Ka value is usually larger than your Kb, you're going to end up with an acidic solution. Okay, and the Kb for the ion is approximate to the Ka, the solution will be neutral. So you have equal amounts of Kb and Ka, then that's where you're going to end up with that neutral solution there. Okay. All right, so taking a look at the oxides of these elemental states, you can kind of see that if I go ahead and combine a lithium oxide, a sodium oxide, or any of those on the left, usually you're going to get a basic solution. Okay. Now, if you take a look on the right-hand side, any of these oxides are going to be acidic, and you're going to get some amphoteric ones if you look at some of the aluminums and whatnot. So carbon dioxide is a great example. You add in some water, you're going to make carbonic acid. And so this is some of the examples where it's a pretty acidic situation. So whenever you have carbon dioxide in the air, and you got, like, for example, a lot of this global warming situation, not only do you have rising temperatures in the world, but you also have a situation where you form acidic compounds. And specifically, this actually works in water when you form that carbonic. Now, N2O5, which is here, it's also going to be acidic as it gets into water, forming nitric acid. So again, these are different ways in which you can go ahead and begin to start with making these acids. So the definition of an acid from the Arrhenius definition basically is anything that produces H3O in water. Okay, so if you take a look at a Bronson acid, it's basically a proton donor. They're pretty much saying the same thing, but one of them actually gets a little bit more specific. And then you have the third definition, is called your Lewis acid, basically, which anyone can accept electrons as an acid. And so the Lewis base is something that can donate electrons. So again, in terms of the naming of these, it's important to know the differences between each one. And so if I go ahead and write down a Lewis acid, for example, I write down that's H plus OH minus, and what you're going to end up getting is the base is going to be the one donating, so you're going to move that over, and then you're going to end up with the HOH molecule. Okay. So in this specific case, because the base donated to the H, that's going to be considered the base. You form that, and then you end up having, now here's another one, NH3. So again, you got to figure out what's actually happening here. And if the N goes in here, because it's got that lone pair, you're going to form NH4. And that's your acid, and that's your base, and then you have an excess positive charge. So that's why when you get an NH4, you basically are going to have that situation. Okay. All right. We're not going to talk about Lewis bases, but that's going to be ending. So please go ahead and make sure you do the assigned questions. Thank you.